This is a production of Cornell University.
And the first thing, well, maybe not the first thing, but the first thing that most people see when they start digging in the soil is actually what they feel, not actually what they see. Okay, when you have a big soil cut or you're looking at the wall, the first thing that you see is colors. But usually the first thing they do is you feel what it feels like. Okay, does that make sense? I mean, when you guys start playing with soil, you're sort of feeling it, right? Yeah, sometimes you're looking at it, but you're really sort of feeling it. Okay, and that feel comes from basically this half of the soil. Okay, remember me talking about this, I want you to think of soils as a volume. Okay, and an idealized soil, basically, let me put this to, I have to look at the holes. In an idealized soil, basically 50% of this material is solid material and 50% of it is void. Okay, so today what we're going to do is we're going to start talking about this solid, and we're going to focus mostly on the mineral component. Okay, that mineral component is that stuff that you feel. That organic component is that stuff that you feel, and they have very distinct feel. Certainly, you guys, when you guys were in kindergarten or grade school and you went to art class and made pots and pinch pots and things like that, you know what the feel of clay is, right? It's that sort of sticky, smooth type of feeling. Okay. You also know the feeling of sand, right? Sort of that gritty. I mean, sandpaper, the grit. You go to the beach, you can feel it. It's got a very distinct feel, right? Okay. Well, what we're going to do today is we're going to sort of talk. We're going to start talking about it, and we'll finish it up on Monday. We're going to start talking about this, and when we start talking about it, we're really going to start talking about particle size. What is it that's in this material? Okay. And when we start talking about particle size, we're really talking about coarse materials moving into more finer material. Okay, so if you have a volume of material, you can certainly imagine there are boulders in there. And from boulders, you can go to gravel or large rocks, and then you can go to sand-sized materials. And then you can move to silty type of materials, smaller. And then ultimately, you're going to get to the really small stuff, which is clay. Does that make sense? And we've sort of separated that out. Okay, so we have coarse fragments. Basically, we consider coarse fragments anything larger than 2 millimeters, and that's the boulders, the gravel. And then anything that's smaller than that, we call the fine earth fraction. And there is a reason why we break these things out. Okay? If you think about a volume of material, and you think about the size of the material that's in that volume, you can certainly imagine the smaller and smaller and smaller the particle is, the more that particles that make up that volume, the more and more surface area you have in that volume. Does that make sense? Does that make sense? So here I have a cube, basically an 8-centimeter cube, okay? And it's made up of one material. It's just one solid piece. Now if I take that cube and start cutting it up, the volume isn't changing, but the surface area is, right? Now, do you guys remember me in the very first lecture talking about, I don't have that slide at the moment, me talking about the spheres and about the interface, soil's the interface of hydrosphere, the lithosphere, the biosphere, and the atmosphere? Okay. The more surface area you have, the more interface you have. It's that edge effect, right? So it turns out that why we think that 2 millimeters is the most important break is that's the point at which the surface area becomes large enough that it has a stronger influence on that dynamic. Okay, I have a piece of gravel. Yes, I'm going to have interactions between the gravel and the larger world. But if I have a same size gravel, but I have a same volume as that piece of gravel, but it's sand, you can imagine how much larger that interface is with the world around it. Does that make sense? Okay, and that's why we have this break at 2 millimeters. Now, there's a lot of technical jargon that goes with it, but basically, there's a lot of different standards. But you'll note that depending upon what standard it is, they all sort of have this break at 2 millimeters. It doesn't matter whether the USDA, you're the British standards, or you're the engineering people, it's always at 2 millimeters. Basically, all of these groups sort of agree that this is the point at which you're having more interaction because of that surface area interface. Okay? Now, that's the first thing I want to sort of convey. The second thing I want to convey is once we start talking about these finer particles, once we start talking about these sand, silt, and clay particles, yes, we are talking about the size of the material, but we're also talking about something else. Generally, the sand-sized particles are roundish. I have it represented up there like a beach ball. Okay? Sand is that larger segment. Okay? As you get down, you start moving into silt. And the breaks, here, let me put it back up here. So sand basically goes down, starts down from here, from 2 millimeters down to 0.05 millimeters. And we got different grades of sand, but basically from 2 millimeters to 0.05 millimeters, it's sand. From 0.05 to 2 microns, it's silt. And anything smaller than 2 microns is basically clay. Now, that's the size differentiation. But it turns out that there's also a shape differentiation. And this is really important as well, not just the size. The sands are round, but it turns out that the silts and clays are more disc-like. They're flat, they're platy. Now, that is going to dramatically influence how that arrangement of volume is made. Okay? Imagine I have round objects. Okay? They're going to pack a certain way. Does that make sense? Okay? They can pack sort of well sorted, they can pack tightly packed, but they can pack, but they're guaranteed that there's going to be holes and cracks in them. It's guaranteed because the way they pack. But if I start packing flat things together, what's going to happen to these spots in here? Any thoughts? It's going to dramatically decrease for the same amount of material that's in that volume. Okay? So if I start packing, I've got balls, imagine I've got a can and I'm throwing ping pong balls in them. Okay? Imagine I have that same can and I'm throwing dimes in them. Okay? The size and the amount of those pores are going to be dramatically different. Okay? And the arrangement of them, how the pathways are between those pores. So let's go back to this slide. Okay? This slide sort of gives you an idea about the shapes of them and the relative sizes. This is a sand size, silt, clay. Okay? Better way to sort of remember it is basically looking at a beach ball, a frisbee, and a dime. Okay, that's the relative size and the relative shapes. Now, you can certainly imagine that if I'm in a soil, it's not going to be just pure one thing. Okay? These sands, silts, and clays, we basically call these soil separates. Separate particles, separate grades of size. But you get out into the real world, and you're certainly going to imagine that you have mixes of materials. Right? These mixes of materials basically make up different soil textures. Has everybody heard the term texture? So this is when we start talking, well, it's a sandy texture or a loamy texture or a silty texture. Okay? And this is where we're going to start talking on Monday. Okay? Questions?
This has been a production of Cornell University. On the web at cornell.edu.